Good morning everyone. My name's Ian Murray. I'm an Associate Professor with Curtin University in Perth, Western Australia, and today we're going to be running through a few things on the Internet of Things. I hope we actually managed to get connected and everything has actually happened live, but we've got this recording for you anyway, either just in case or something for you to watch later on. Nazanin, who is over there with you today, she's one of our technical staff and teaching staff working in the area of networking and the Internet of Things. She'll be there to help facilitate and make sure you can get all the labs done as smoothly as possible. Hopefully everything worked and we actually got to do this live rather than just from this recording. So we will make a start. Okay, so the Internet of Things. What is it? Why is it relevant? How can it be useful to engineers of all persuasions? It's not a new area. Networks have been around for 30, 40 years. Embedded systems connected to sensors, they've been around for probably longer. But it has all just sort of come together with the changes in technology, particularly with the availability of bandwidth, the cost of sensors, and the power of the embedded controllers that we're using. So, first of all, let's have a look. Why is this relevant to all engineers? So I'm going to play a short video here made by Cisco. It's particularly good because it does show how the Internet of Things works in a city environment. We're going to cover things on general network and communication a bit later on because that is a key aspect to the Internet of Things. And of course, we'll go into details of what that is. So, our first movie.
As the world continues to urbanize, with 180,000 people a day moving into cities, the competition between cities will continue to grow economically, environmentally, and even socially. The cities that embrace technology will surface as the winners.
Think about it. Only 1% of what can be connected is connected today. Imagine the possibilities. The Internet of everything has arrived and is ready to change the world.
Cisco is extremely excited about Barcelona because the city is utilizing the Internet of everything. By connecting its people and things to a city Wi-Fi, Barcelona is creating new services, richer experiences, and unprecedented economic opportunity for its people, for its businesses, and for its partners.
Barcelona is a social dream, and technology is able to make this social dream possible.
We face in Barcelona the very same problems that every city in the world faces. So we want to tackle those problems with technology.
What we're trying to put in place is a common solution for all the cities of the world.
It is estimated that 40% of traffic in city centres is caused by cars trying to find a parking space. Now, in-ground parking sensors communicate with devices in cars to help vehicle owners quickly find an available spot.
Putting sensors in parking spots allow us to get less cars, less traffic, people happy, so that the city becomes a more livable place.
We have to make it possible for people to understand that Internet might be changing their daily life to improve it.
We transform the experience of wasting your time waiting for the bus into a full contact with the city. People can find information on routes for the bus, plus information on the area, business, commerce, shows.
Barcelona's citizens not only enjoy the smart bus stop experience, but are also able to maintain their Wi-Fi connectivity while on the bus or underground train. This allows citizens to get the same sensation of connectivity as they get at home. Understanding that much of a city's energy waste comes from less than optimal use of lighting, Barcelona is installing highly efficient streetlights which are dynamically managed to save energy, optimize maintenance, and provide a safe environment for citizens. A city-wide network of sensors provides city officials with concrete information so that they can make decisions based on real-time data.
Getting information on the flow of citizens, on noise, on pollution, on traffic, on weather conditions allows cities to streamline the city operations, reduce costs, and also improve overall sustainability. Economic sustainability, social sustainability, and environmental sustainability.
Barcelona can generate a blueprint of what the cities can become, and this is what gives sense, full sense to what we're doing in Barcelona right now.
Technology is for people, technology is for using it, and technology is for improving citizens' lives. We are sure that the Barcelona of the future will be even much better than it is now.
Smart cities represent places where people will want to live. By connecting the unconnected, cities will be completely transformed. These are the cities that will harness the power of the Internet of Everything.
Right, so from that video we can get a general sort of idea, just out of interest, what the Internet of Things is doing for city management. Everything from managing traffic, looking at parking, checking to see if the bins are full or not, and only sending the trucks out to empty bins as they're required. And we start to see, just from that very general introduction, that this is a big thing that is going to impact many of our careers and the way we design things and the way we do things. Getting back to the basics though, we've got to think where this has come from. And looking at the history is terribly important because it shows us how things change rapidly and where we're heading. Here I've got the 4 phases of internet evolution. If we look back at the first phase from the 60s and 70s, we had the connectivity, then we moved later into phase 1, which is how we digitized access to information. Email came of age, the World Wide Web came into being, we were able to search for information. Information became available to everyone, no matter where you were, as long as you had access to a computer. Then in phase 2, we started moving things a little bit further along. It wasn't just the information, but businesses started getting in on the game. We have the beginning of e-commerce, the digital supply chain. Now this part, the digital supply chain, is absolutely crucial, a very big part of the Internet of Everything. It helps us to develop systems for supply of materials in manufacture, but also in many other areas, including agriculture and medical practice. We have the collaboration, exactly what we're doing here. We've got a video conferencing going, things that didn't exist before. And the things started picking up again when we'd gone into this collaborative experience. The collaborative experience is our social media, the impact that individuals can have on society in general through social media. We have the cloud. The cloud's nothing new. We've got to think of the cloud as basically you're just using someone else's computer. This is how it all started. We had mainframe computers, everyone connected to them, the storage was off somewhere else where we hired time on that computer and it kept the storage there. The cloud is a very, very similar thing. It's just a more flexible, slightly more advanced way of doing things. And because we have the networks with the bandwidth and the speed and the capability to move data very, very quickly and in large volumes to someone else's location, it means we don't actually have to keep it stored locally, and that overcomes the storage issues but creates a lot of other issues which we will have a look at a bit later on with security. We have video, YouTube, the explosion of YouTube. What we're doing here, for example, with the recorded videos is a part of that. We can do online learning, we can provide information to other people, we can demonstrate our products, we can have guided tours through video on the internet. So we have that collaborative space where we can work together. We have video, audio, cloud storage, and we can all work together on shared documents. Think Google Docs. Now the final phase that we've got so far, and it is a so far, is the Internet of Things. Now what we're doing here is we're trying to connect all of these previous parts into one logical progressive step. So we have people. That is the main thing. We want to deal with people. People are the important part. Data on its own is useless without the people to interpret it. So we're going to make it easier for people. We have a process. For example, as we said, we've got the supply chain. Supply chain is a process, and using the Internet of Things to improve the process to make things more efficient is part of the Internet of Things. And then we have this large area of big data. Big data is something which we don't understand, we're not using particularly well, and we don't have good ways to handle it. And we'll be talking about big data separately a little later on. And then we have things. The things are the things that collect all the information that we need. Now that can be a video camera, it can be an inertial measurement unit, it can be a stress gauge on a bridge or within a building. Things are the things that collect data, and these are what we're going to be playing with a great deal this weekend. Developing the systems which will collect the data, which we can then do things with and make intelligent decisions. So networks in our past and daily lives, if we look at the uptake, this is quite interesting in that we looked at the fixed computing back in the 1990s, thereabouts. You had to go to the device. We all had a desktop that we used. We'd go to that desktop, we would use the data, we would collect things, we would analyse things, we would do our designs, whatever it was that we wanted to do on the computer. But we had to go to the computer. Things started to change. We had mobility, where we have laptops, we have iPads and other tablet type devices. The ability of our phones to do a lot of the work with us. We can have our email, we can browse the web, we can do a great many things just on our mobile phones. So we started to have mobility. Salespeople are out there with their iPad or their phone, they're taking orders, they can get stock lists, they can look at availabilities and interact directly with the client with no lag between the information being gathered and being passed on to the client. Now we're starting to get into the Internet of Things. This is the age of devices. This is where things are talking to each other without human interaction. So we have our fridge as a bad example, which I think I've got a video on shortly. In the fridge, it works out how much milk you are normally using in your daily life. It decides, you're running low on milk, so I'm going to order some more for you. The fridge contacts the supermarket contacts the supermarket fridge. It pulls out some milk for you, gets it to the checkout, sends you a reminder to pick it up on your way home. You stop at the supermarket, you pick up the groceries that your fridge has selected for you, and you head off home, you put it in the fridge. The fridge logs that entry of milk, and it now knows how long it can last before you need to purchase any more. It'll also check expiry date for you, make sure that you've got fresh milk, not sour milk, and ensure that you've always got what you need on hand as you normally use it. That's a trivial example. If we start to apply that to general industry, things become very, very interesting. We can order parts for our manufacturing line as we require them. The supplier will have an idea of your usage, so he will only start manufacturing the items as he thinks you start to need them. And this is handled by your production line talking to the supplier's production line. It talks to the robots which are doing the manufacturing and controls the inventory without a human being involved. This is where things are heading. This is where the great growth is going to be in manufacturing, but it also works in other areas, as we'll see with some of our case studies. So if we actually look at the numbers here, back in the 90s, there were hundreds of thousands of devices connected to the internet. As we moved on to the 2000s, we have a couple of 100 million devices connected to the internet. Currently, we have somewhere in the vicinity of 10 to 12 billion devices connected to the internet. And it's envisaged within the next 18 months, 2 years, that there will be 50 billion devices connected to the internet. And these are generally things that weren't normally connected to the internet previously. And we'll have a look at some case studies on that shortly. If we go back a bit further and we have a look at the evolution of the internet, the bit that connects us all together. It started, as I'm sure most of us are aware, with the ARPANET, the Advanced Research Project Agency Network. It was established in 1969 and only had 4 computers connected together. This is not that long ago. I was 7 years old back then, so it's within most of our lifetimes. It had a very slow evolution until 25 years ago when it started to become adopted by the general public. And we can see from this graph, things have grown very, very rapidly in recent times. From 2012, 8.7 billion devices connected to the internet, with an estimated 50 billion connected in 2020, and probably earlier. That's been revised recently. Along with the issue of the number of collected devices, we have what they're doing. They're collecting data, they're processing data, they're transferring data, and the data is a key issue that we have to deal with. So if we have a look at where the data is coming from and how much there is of it, we can see from here the years 2013 to 2020 and the amount of data that is being produced by each type of device. Our fixed communication has had slow but steady growth over the years. Our mobile communications has grown fairly rapidly, but by far the largest communication is our industrial devices. This is where we have our machine-to-machine communication, a key feature of the IoT. So why the IoT? As we've seen, we've got a lot of data coming in, we're going to make more use of it, but the problem is when we have this much data, we have a great deal of difficulty dealing with it. When we have exabytes of data, it's not humanly possible for people to look after that. So we're wanting to receive more data. And when we receive this data, we want to control things, whether that be your fridge, for the simplistic example, or your manufacturing line. It is still things that we want to control. We don't want to have to handle all of this control manually. We want to automate things. And generally we want to make things faster and easier. I've got an example here just of a little dashboard. Now this is a dashboard that collects data from silos within the San Francisco area. Collects information on what's in them, how much they weigh, and displays as a dashboard, which makes it much easier for the operators to understand very quickly and very easily what is happening within their environment. Dashboards like this, they take masses of data from many sensors, brings that data together, performs some analysis on it, and produces a result that is easily interpreted and acted upon, and that's a key factor. It's acted upon by human beings. This is what we want to use the Internet of Things for. The IoT stack looks a little like this. The IoT stack is a way that we look at how things are processed within the Internet of Things. Problems come about because we have a very large array of sensors. The sensors collect the information, and currently they are generally sent off to the cloud for processing. This is an issue. The issue is that we have large amounts of data being collected at the sensor point. It's then all transported up through a limited network infrastructure to the cloud for processing. It means we have latency in the information reaching the point where it's processed. We're using bandwidth for tasks that we may not need to use bandwidth for, and we're sending superfluous information that doesn't really matter. So if we look at a room temperature sensor, for example, it may only sample something once every minute, but the temperature doesn't change rapidly. So we can sample it every minute, but really we only want to send the update to our control system when something changes. The temperature starts to rise or it starts to fall below the threshold. We want to send information at that point, not all the time. Another very good example is motion detection. We have motion detectors within our room. We have videos attached to that motion detection. Do we want to upload all of the video, the entire video stream, which may be just of an empty room, nobody in it, nothing happening, and we're sending megabytes of data up the channel to be processed by the system within the cloud or the processing cloud, even though there's no change happening. So we should really be doing this locally, or only when movement is detected within the room itself. Unfortunately, as this graphic shows, we have sensors. There's not a lot of local processing happening at the moment. That is changing as the abilities of our embedded systems sitting at the edge, or what's called fog computing, processing at the edge of the cloud, is starting to happen. We can then either locally store, send through the network, and then store in the cloud, or we can just send directly to the cloud some pre-processed data. And again, this is what we'll be looking at with some of the lab exercises that we're doing today and tomorrow. We'll look at doing the edge and fog computing, so we start to process the data prior to sending it to the cloud, and that is crucial for reducing bandwidth because that is still limited, and also to improve the latency of things. If we have to send things to the cloud, there's latency in the network delivery, and we have to be certain that we're having things happen on time. If we can do some processing at the edge and take action at the edge from that processing, it decreases our latency, makes things much more efficient. Looking further at the IoT and its significance, the IoT is a network of physical objects accessed through the internet. Fairly straightforward definition. Objects are using embedded technologies to impact with the environment, and again, this is something that we'll have some examples of and you'll get to play with within the labs. And the overall aim is to improve the quality of life of people by automating systems, and hopefully we'll be able to do that. So some definitions. These are actually from Cisco, a very large company. I hope you're all familiar with them. If not, ask Nash, she'll fill you in on all the details with Cisco. The definitions: things are any device that connects to the internet or each other, very important, they can just connect to each other, and collect data for analysis. Data is the information that we collect from these devices on the network. Process is responsible for delivering the right information to the right person at the right time in the most relevant way. So the process is bringing all of that data together, performing some action on it, reducing the bulk of it. We don't want that massive information passed directly to people. Computers can handle that better, but we are better as people to make the decisions. So we need to gather that data and transfer it to a person in the most relevant manner. And then we have people. People are the nodes on the network. We are the ones that make the decision. We are the endpoint where the information arrives finally. Okay, with these connections, we have several terms that we need to understand. As I mentioned, part of the Internet of Things is machine-to-machine communication. This refers to the direct communication between devices on any communication channel. It can be anything from industrial instrumentation, enabling a sensor to meter or communicate the data it records, whatever it happens to be, and application software that uses it. And this is all happening without human interaction, something that's very different to what we've been doing in previous time. We have the communication or the connection, machine to people, and this is how the machines tell us what's going on, provide concise information so that people can take action on it. And finally, there's the people to people. Again, this is the traditional internet that we have, me talking to you now, sending an email, web pages, etc. So there are the three main forms of connection that we have. Okay, the IT in operation. In any IoT system, we have, as we've mentioned, a group of sensors that will collect the data. Some of that data is processed and stored locally at the edge or fog network. Not as much as we would like, but some of it is. Now, we need to use a number of protocols to perform the network functionality, and we'll have a brief look at those in the networking section a bit later on. But these are not just the standard networking protocols that are used like TCP/IP and Ethernet. They tend to be very similar in operation, but they do have some significant differences. We require an internet connection, and this is where the standard protocols come into play. That's to get the data back to the cloud or the processing nodes. And data is going to be processed and stored in the cloud as well. So, looking at these in individual pieces, we have sensors. These are often analog and they need to be converted to digital, filtered, and other processes happening on them to make the data of some use. And again, when we get to the electronic section, we'll have a bit of a talk about those. Usually the sensors are ultra low power and they've become very, very cheap nowadays. Welcome back. You'll probably notice slightly different surroundings. I'm back in my office now, and we'll continue with looking at actuators. Actuators can be very simple devices such as motors. They can be electronic, hydraulic, pneumatic, and other forms as well. But generally these are the devices that take the sensor data that we've analysed or manipulated in some way and take action in the real world. We'll be using a simple one of these in the labs, just a servo motor to translate some readings from an inertial measurement unit over to physical movement of the servo motor itself. We also require controllers. Controllers are the device that actually do the reading. These can be quite complex devices or very simple devices. They range dramatically in prices, we'll see shortly, and also they vary dramatically in their capabilities. Controllers are generally a programmable device, such as a microcontroller. Usually we try to use very low power devices, and they may have an operating system, or in fact they may not. Not all computers have operating systems. And again, we shall look closely at that a bit later on. The controllers receive raw data from the sensor and send a set of instructions out to any actuators that are attached to the system based on that sensor's input. Microcontrollers come in a general sort of form. Most appear like this. They are a low-powered small computer with some RAM, that's random access memory, a CPU, and the I/O ports, ways to get information in and out or control things, read information in or control some actuator as an output. Uses an embedded system in consumer products, and this is the type that has no operating system. An embedded system acts as a single-use device. It's programmed to do a particular task, it does that task and nothing else. The computers we use in our laptops and desktops, they are general purpose computers and their purpose can change. We use the simple microcontrollers, the embedded system, purely to read the sensor data in and to provide some output to an actuator or other device. Generally, they're in this sort of architecture where we have a CPU, a shared memory which stores both data and program, and we have some I/O ports which do our input and output, of course. This is the von Neumann style, but there are others which have a separate program and separate data memory, the Harvard or modified Harvard processor. The ones we're actually looking at are along these lines. These are suitable for a sensor environment. They're a microcontroller, generally do not have an operating system. They have usually a significant amount of I/O, a number of pins that we can use for input and output, and they range in price dramatically. So the one we're using today is the Arduino Uno. This is a sort of a mid-range device. It's reasonably powerful. We'll look at the specifications in a sec. It sells for around $30 to $40, making it relatively expensive for a sensor environment, but they're a fairly good development platform, aimed mostly at the hobbyist type market, but are also quite useful for prototyping in other areas. The Arduino Uno has an Amiga 328 as its processor. The launchpad in the bottom right corner has a MSP 430 from Texas Instruments, and that's a mixed signal processor. So it allows us to work on both analog and digital signals, something like a signal processing chip. Microcontrollers that are suitable for sensor and processing environment. Some of them are listed here. We're not going to go or use these in this particular lab set, but the one that's of interest there is the Esperino. The Esperino, rather than using a normal programming language like C, uses JavaScript, which is something that's very much web-based. That can have its uses, but it's inherently insecure, and that's a big problem in the IoT, and it's not particularly efficient as far as its processing goes. The other type we'll be looking at and using is the microcontrollers that are suitable for processing and have the network environment. The Arduino we looked at previously, it doesn't have any network connection. You can't talk to the internet directly from one of those. You need to either plug it into another board or add a component to the Arduino Uno. We'll be using the Raspberry Pi, which is a fairly generic, full-featured computer. It runs a Linux operating system, and it can run others as well, but generally we run a Linux-based operating system. It has a significant amount of memory, large processing power, and a full network stack. The Raspberry Pi 3 that we are using is quite cost-effective and comes with the wireless Ethernet, so the standard one we're used to in most networking, 802.11n, and it also has the Bluetooth stack, allowing us to connect a personal area network, which is quite convenient for some of the sensor-based applications. As we can see, there's a large range of them around, ranging in price anything from $35 to several $100s, and you pick them based on your processing and connectivity requirement. Again, these are standard off-the-shelf boards that we can just buy at the local electronics store. Things to remember with these devices: we select them due to their low power consumption, their processing power, and their connectivity. So generally they are limited in both memory, the power we can draw, so we have to have some supply, and if it's out in a field, would need to be battery, solar, wind, energy scavenging, some other method of powering the device. They are limited in processing power. Again, we have to limit the processing power so that they don't draw too much electrical power. They usually have very limited bandwidth. The connection to the network that they have is usually fairly limited. So if we look at Bluetooth, we're lucky to get a couple of 100 kilobits per second out of a Bluetooth connection. And they have very little throughput, very limited throughput. So even though we may get a reasonably high connection speed, the processor itself can't handle large amounts of data. So these are the limitations on our processing platform. Now, once we've looked at the processing platform, we also have to examine how we're going to connect things. Networks impact our daily lives. We use them in the way we learn. Here we go, we're doing it right now. We use them in the way we communicate. Most people use Skype nowadays. We use WebEx, such as what we're doing at the moment. It affects the way we work. We use them continually in work. And also it affects the way we play and what we do in our relaxation time. The picture here, by the way, is one of our laboratories that we use for remotely teaching networking technologies. This is available to students 24/7, no matter which campus they're located at. So students in any of our campuses can access real equipment, and that's the key point, over the internet. It's delivered to them via an internet browser, and they can interact with the equipment that way. Traditionally, we use client-server networks, and there's a depiction here. All of our comms is based around the same principle. So we'll look at the ones we're most familiar with, and here we have a group of computers connected to a switch in the middle, which allows a connectivity between each of those devices. Okay, so let's have a look at the components in the network. Generally, there's three categories that we deal with. These are the devices, the media, and the services. So for our devices, it can be all of our end devices such as the computers. It can be the switches and routers which connect things up, our IP enabled phone. We have the media, and the media varies, and this is kind of important for the Internet of Things. We have usually a wireless media involved to communicate to the broadcasting node, which is our microcontroller, but it can often be a cabled, so we have a cabled or wireless Ethernet. And finally we have the services. Services are the things like your web server, our database which will sit at the back end to store the information that's being processed, and mail servers, etc. To be able to communicate, we need to have some rules, and it's the same in all communication, whether that be computer communication or even the way we're talking now. We need to identify the sender and receiver. We need to have an agreed upon method of communication, say face-to-face or telephony or over the internet like we're doing now. We need to have a common language, which in this case is English. We need to work out the speed and timing of delivery. We need to confirm or acknowledge requirements. So we need to have a handshaking arrangement so that we can decide how fast we're going to transmit, what encoding we're going to use, and various other attributes of our communication. Message encoding is done in a fairly standard format. We have our message source, say for example an email. We encode that in some manner. We turn it into ones and zeros or radio waves or light. That is then passed to the transmitter. It's transmitted across the media. It's then received. We need to decode, and we get the message at the destination. Probably the easiest way to look at this is to have the example of old-fashioned mail. Not sure that anyone uses this anymore, but it's a good way of getting across the idea of message formats and encapsulation. So for example, if we're sending a letter, we need to have on the outside of the envelope, which contains our message, some information. This is where we're sending it to, where the recipient is located. We need to also have a return address in case it doesn't make it to its intended destination. We need to be notified that it didn't make it, so we can take action to either retransmit or find out how to get that message across. This is not always the case in all protocols, but is a fairly common thing to be doing. Within the message itself, we need some form of greeting. Now, normally we would start off with "Dear Sir, Madam," or "Hello, how are you?" We need a similar sort of thing to say we are now starting to transmit data. So we have a flag or some indication at the beginning of the message saying our message is about to start. We then put in the content of that message, and we have a end of message indicator to say, right, we've sent everything, we can now finish, so that we know that this is encapsulated within the message. To do this, we have a number of protocols, and protocols are very simply a set of rules that govern how two or more communicating entities in a particular layer, and we'll mention layers shortly, interact. It defines the messages that can be sent and received. It defines what actions are taken when certain events occur, such as a dropped or out of sequence message. Your email message gets sent into the application layer. The application layer knows how to receive that information. It then passes that block of information to the transport layer. The transport layer is responsible for setting up the logical connection between the endpoints. So this is something like a phone call. It'll connect you to the end user logically, not physically but logically. That is then passed to the internet layer. The internet layer then decides what path that message is going to take. So it looks which wire it goes down, which route it goes through, which telephone exchange your message goes through, and determines the best path possible given the constrictions of the that particular protocol. And then we have the network access layer. This is things like Ethernet. The network access layer decides how we physically access the media. This is critical in things like wireless. Wireless is a shared media. We all use the same airspace to transmit our messages. So we need a fair and contention-free or close to contention-free method of accessing the airwaves to be able to transmit or receive our data. The network access layer performs that function. Basically, it looks to see if anyone's transmitting, and if they are, you don't transmit, you wait. If you do find that the airways are free, you send a request to send. Is it okay to send? Everyone else sees that, backs off, doesn't try and grab the media in the meantime, and then allows you to send. So it looks after the access to that physical media. So in summary, here's a TCP/IP reference model. The application layer represents data to the user. It's how we interact with the protocol stack from our client applications. The transport layer works like the telephone system, provides an end-to-end connection between users in a logical manner, not in a physical manner. So it's just looking from one end to the other end and doesn't know how it's going to get the connection done between, because that is the job of the internet layer, the IP layer. This defines the best path through the network, and that is not necessarily an optimal path, but it is what the network decides is the best path. And then we have the network access layer. This layer controls how we actually access the media that we are using to transmit our data, the ones and the zeros, or the light pulses, or indeed any other form of communication that we're using. Right, so now we've had a very, very brief look at networks and how we use a network stack to arrange communication. Let's have a bit more of a general look at the Internet of Things. And I've mentioned a rather trivial example of checking for milk in the fridge. And we've got a nice little video that will show an example of this. And it's only for sort of home application, but I think it gives a fairly good idea of how things can interconnect and leverage off each other in the Internet of Things.
This is the cat that drank the milk and let in the dog that jumped on the woman who brewed the coffee.
Brew coffee.
That woke the man who was late for work.
All right, I gotta go.
And drove the car
Driverless mode engaged.
that found the parking spot
Find parking space.
Parking space found.
that alerted the door that opened the control room.
Hey, Bob.
That secured the data, that directed the turbines, that powered the sprinklers, that watered the grass, that fed the cow, that made the milk, that went to the store, that reminded the man to buy the milk, that was poured by the girl who loved the cat, that drank the milk. The Internet of Everything is changing everything. Cisco, tomorrow starts here.
Right, this next video is more or less an ad for Cisco, but it's worth having a look at just for the insight that it gives us into industrial applications of the IoT.
Whether you're a manufacturer assembling cars or packaging a line of cereal, imagine if you could deploy new, secure, innovative solutions that could increase employee productivity 10 to 50%, reduce unplanned downtime 30 to 50%, increase your flexibility and agility to quickly change production lines and introduce new products, and lower your networking costs 10 to 15% and cabling costs for mobile machine tools up to 95%. That's the Cisco Connected Factory solution, a fully tested and validated converged architecture that securely connects the plant floor to the enterprise to solve today's toughest manufacturing challenges. Let's look at an automotive plant to see some practical examples. A connected factory gives manufacturers the most flexibility to coordinate production changes across the entire factory, not just individual machines. Each affected zone, from the enterprise to the plant floor, is alerted of changes in real time through mobile devices, video monitors, and HMIs that communicate over the converged network. The information is also linked back to the entire supply chain so that each step in the manufacturing process can quickly respond as needed. Traditional paper scheduling of machines can also be a problem when changes are occurring multiple times a day. However, a converged network lets you connect all of your systems, from ERP to ordering to scheduling, right to the machine's HMI and react to changes instantly. The Cisco Connected Factory solution turns your factory into a wireless environment that creates new communication opportunities between machines and people located throughout the plant. For example, the time it takes someone to walk down a line to investigate a machine problem can be very inefficient and lengthen downtime. But given a mobile tablet or smartphone, a maintenance worker can see a machine's control data remotely and diagnose a problem in real time from anywhere in the plant and bring the right people and parts to the machine faster to get it back into service quickly. You can even send HD video and machine data to experts around the world to help diagnose and resolve problems without having to fly them to your plant. And tools that are frequently moved across lines no longer need to be tethered at each location, but instead use the wireless network, dramatically cutting the costs of replacing cables. Now imagine your connected factory with the intelligence to perform more fine-tuned, predictive maintenance and to control machine-level energy usage to improve OEE and lower costs. Analytic engines can communicate with machine sensors to stream detailed operational data between the plants and higher-level systems for real-time visibility into the ongoing health of each robot. This helps prevent problems before they occur and achieve near-zero downtime as a result. And with real-time visibility into energy usage, manufacturers can more easily take actions to avoid peak loads, better manage energy consumption, and cut plant energy use by 10 to 20%. To help factories become more secure from the plant floor to the enterprise, Cisco's Identity Services Engine embedded into the entire architecture facilitates risk avoidance to protect against security breaches that can penetrate beyond individual machines and into the entire organization. Plus, Cisco enables new business models, such as machine-as-a-service capabilities that run securely over a Cisco or partner cloud to speed problem resolution and increase factory uptime and output. And this just scratches the surface, as the possibilities for the smart, connected factory are nearly limitless. So, how do you create a connected factory of the future? It begins with a foundation that consolidates all of your aging, disparate, and proprietary plant floor OT networks and converges them with your enterprise IT network to create a fully connected, converged plant-wide Ethernet. Now, your factory can leverage the Internet of Everything, a whole new approach to intelligently connect people, processes, data, and things, from smart sensors in machines to cameras, scanners, and personal mobile devices across all entire manufacturing operations. New wireless solutions can augment your existing wired infrastructure to enable new capabilities. Next, integrated Cisco factory security is enabled across the plant for both physical and digital assets, enabling risk mitigation from cyber attacks and secure remote diagnostics and repair of equipment by vendors. Now you have a solid infrastructure for new application enablement through Cisco and industry-leading partners to help create positive business outcomes for your smart factory of the future. So, are you ready to securely and reliably connect your information and operational technology networks and start creating your connected factory with a high benefit-cost ratio? Then visit us on the web to learn more.
Okay, we have some challenges in the IoT. Those are security. It's not terribly secure, and if we're putting out many devices in an area, then security becomes a rather significant issue. We have the issue of privacy. With the IoT, we've got devices everywhere. They're tracking our movements, they're tracking what we're doing, tracking our medical records, and this causes issues with privacy. There's reliability. If these are in key positions, items need to be reliable, and this again comes down to how much charge we can have, how much charge we can store, how long they can run without maintenance. We need to have some open social and political discussions on this, because they are taking over, they are monitoring a lot of what we're doing, and again harks back to the privacy but also the ethics of the Internet of Things. Is it ethical to track people the way we do? The network protocols aren't designed for this large transactional, large amounts of data, continuous data being sent to areas for processing, so we need to look at ways of improving the protocols, and that's underway with things like LoRaNet. Storage is also an issue because of the massive data, and we'll have a look at that in the big data section, and also the analytics, and again we'll have a look at that in the big data section that we're looking at later. Okay, so what we'll be doing is we're using some software for prototyping. We're basically going to be using the Arduino, which is controlled by the Raspberry Pi, so Arduino's a little microcomputer. Raspberry Pi is a normal embedded computer, and it controls the Arduino for us, so it makes life a little bit easier. And we're using a package called WilyOdrin. WilyOdrin allows us to do graphical programming, which makes that prototyping a little bit easier. Probably not the best thing to be using for a production type development due to its inefficiencies, and has a few funny little quirks which I'm sure Naz would be happy to explain to you later. But it's a good development environment for our use. There's many professional programming environments that we can use, and some of them are listed here. You can look them up when you're ready, and other data storage facilities and utilities that we can use. Microsoft Azure is probably one of the most popular ones around. So our graphical programming looks a little like this. It reduces our learning time because it works on graphical blocks, a bit like a jigsaw puzzle. And we can put together our command blocks in the order we like without having to know the syntax, or a great deal of the syntax involved in the programming language. So it makes us a lot easier for development. You'll notice one of the panes on here on the right hand side will actually give us the code, so if you want to write in code directly you can, but it's not absolutely necessary. Okay, so let's get started. This is Fritzing, which is a little application that allows us to lay boards out. We can build the circuits up pictorially, graphically, get an idea of what they're going to look like and where we're going to connect things, and then we can actually build it on the development environment that we're using. And finally, a little bit on what the IoT thinks of you. Alright, have to have a little bit of humour every now and again. So again, can't have questions here because this is a recording. But I'm hoping that we actually made the connection and everything worked, and we did this in real time, and you can just use this as a reference. Thank you. Let's get prototyping.